All right, so the notes ask us to graph r equals sine theta. Now, I'm going to let you use your calculator to do this. So in order to graph r equals sine theta, we're going to have to be in polar mode. So you need to hit your mode key, which is below alpha. And it's likely that you're still in parametric mode, but you may be back in function mode. So if you right arrow and go down to polar and hit enter twice, then when we go to y equals, it's r equals something. Calculator is so smart. All right, so we want r equals sine of theta. Now, you have to use theta, just like in parametric mode, you had to use t's, you have to use theta. And theta is a second or third function of something. It's diamond caret. It's in the same place as pi, but diamond instead of second. And, of course, this calculator is going to make you close your parenthesis. I have no idea what your window is going to do, so let's look at your window. Okay, mine looks pretty good. I would suggest always graphing between 0 and 2 pi, because basically yesterday how we talked about, unless otherwise stated, assume that you're working between 0 and 2 pi. The theta step needs to be pretty small, because that's what's going to evaluate the graph every that. This 1.38 or 0, whatever that is, 1.30, I'm assuming that's like pi divided by 12 or pi divided by 24. It's some multiple of pi or fraction of pi. All right, so I'm going to go for it here. I'm going to graph it. Might need a smaller window. Yes, I definitely need a smaller window. That's why. All right, I think if I go like -2 to 2 for my x's, and maybe -1. Whoops. Maybe like -1 to 3 on my y's. I'll be good. Okay, there we go. So basically what we have is a circle. What does it look like the radius is? Yeah, 1/2. The diameter is 1. All right, so I'm just going to go over here and draw myself a circle. It's a circle. And the reason it looks kind of like an oval is because the calculator screen is rectangular instead of square. Another thing on the calculator, when you graph it, like watch my calculator right now. I'm going to re-graph it. Notice like the order that it graphs in. It starts at 0, 0, and then goes around to the right and comes back to 0, 0. And that's always kind of helpful to know exactly what that's doing. It's kind of good to have an idea of that. It's not something that they usually ask you to draw on the graph, but I think it's helpful to show your starting point and show your direction sometimes, because when we start talking about different points on that circle, it'll help give you a reference of where it is. All right, when theta is pi over 6, so remember we're starting when theta was 0, and then we're going around like that. So where do you think theta is going to be pi over 6? Yeah, kind of on the right. So like maybe about right here. Okay. Is the slope of that tangent line positive or negative? Positive. Okay. If theta is pi over 3 is basically going to be 2/3 of the way through the first quadrant. Is that slope positive or negative? Negative. Okay, given the equation r equals sine theta, I want to find dr d theta, so the derivative of r with respect to theta. So what do you think dr d theta is going to equal? Cosine theta. Yeah, it's not a trick question. The derivative of r with respect to theta of sine theta is going to be cosine theta. All right, at pi over 6, dr d theta equals what? What do we need to do to evaluate dr d theta at pi over 6? Yeah, plug it in. Find the cosine of pi over 6. And root 3 over 2. I'm cool with that. Does that surprise you? No? Okay. I don't know. Okay, let's look at the next one. At pi over 3, well, okay, first off, what does this say about r? R is what? Good. Dr d theta is the derivative of r with respect to theta, so the rate of change of r. So what it says about r is that r is increasing. If dr d theta is positive, r is increasing. If dr d theta is negative, r is decreasing. Okay, if r is increasing, what can you tell me about a point on the graph? What's it doing with respect to the pole? Yeah, it's getting further away from the pole. So in terms of the graph is moving away from the pole. Okay, and then at pi over 3, dr d theta will equal the cosine of pi over 3, which is 1/2. So what can you tell me about r at pi over 3? Yeah, r is still increasing. And the graph, therefore, is still moving away from the pole. Good. If r is increasing, then the graph is moving away from the pole. If r is decreasing, then the graph would be moving towards the pole. Yes, the pole is 0, 0. I should have clarified that. Okay, now what I was expecting some people to be surprised about is that, oh, I guess you weren't surprised, is the dr d theta at pi over 3 is 1/2. But the slope of the graph at pi over 3 is negative. Okay, so that's what I was trying to illustrate, is that dr d theta does not represent the slope of the tangent line. It's the rate of change of r with respect to theta. So, or how fast the particle is moving away from the pole relative to how fast it's moving around it. The slope of the tangent line is still dy dx. Okay, so even if they ask you to find the slope of the tangent line to a polar graph, the slope is not dr d theta. It's still dy dx. No matter what, slope is always dy dx. So, in order to find dy dx, what we're going to have to do is rewrite the polar equation as a term in terms of a set of parametric equations in x's and y's, because to find slope, we have to find dy dx. Okay, from yesterday, we know that x equals r cosine theta, and y is r sine theta. So your r is going to be given to you as an f of theta, like an equation, like in the previous example, or in the first example, r is sine theta. So to write r equals sine theta as a set of parametric equations, x equals r is sine theta, and then times cosine theta. Basically, x is r cosine theta and y is r sine theta, but then you have to plug the equation for r in. So y is going to equal sine theta times sine theta or sine squared theta. Now, given x equals something in terms of theta and y equals something in terms of theta, what's the breakdown of dy dx? Good. dy dx is going to equal dy d theta over dx d theta. So it's just like the parametric equations where you had two equations in terms of t. Dy dx is dy dt over dx dt. Now it's dy d theta over dx d theta. Okay, so we've written theta as a set of parametric equations. Now we need to find dy dx and the slope of the graph at theta equals pi over 3. So I'm going to start by finding dy d theta. So what's the derivative of y with respect to theta? 2 sine theta cosine theta. Good. Just using the chain rule. And then dx d theta, unfortunately, I'm going to have to use the product rule. Okay, so, well, wait, hold on. The derivative of the first times the second would be cosine squared theta, plus the first times the derivative of the second would be negative sine theta. So cosine squared theta minus sine squared theta. That actually is not negative 1. I know where you're getting that, though. Sine squared plus cosine squared equals 1 because of the big daddy. But, right, it'd have to be negative cosine squared minus sine squared to equal a negative 1. So that doesn't work. So unfortunately, dy dx is 2 sine theta cosine theta over cosine squared theta minus sine squared theta. However, both of those are properties from trig. Anyone remember what 2 sine x cosine x is? It's the double argument. 2 sine x cosine x, or 2 sine theta cosine theta, is the sine of 2 theta. Cosine squared minus sine squared is, if you had to guess, what would it be? Cosine 2 theta. Okay, now those are not something that you have to have memorized, but look at what we're going to do here. Is we're going to find the slope of the graph at theta equals pi over 3. Would you rather plug in pi over 3 into the tan of 2 theta, or would you rather plug it into the original 2 sine theta cosine theta over cosine squared minus sine squared? So it gives you a little bit of motivation here. So there's my dy dx. So you like a challenge? Okay. So when theta is pi over 3, dy dx equals the tangent of 2 pi over 3. I can't visualize. Okay, 60-degree reference angle would be root 3, but that's in the second quadrant, so negative root 3. Good. You got there faster than your teacher. All right, so the big thing is that you've got to turn that polar equation into a set of parametric equations.